Take a look at this plastic bottle. It looks completely ordinary. In fact, you've probably held hundreds just like it. Now, take a look at this. Petrol, a liquid that powers millions of vehicles every single day. At first glance, these two couldn't be more different. One is a hard solid. The other is a liquid. They don't look alike. They don't feel alike. They certainly don't behave alike. So, let me ask you something. Could this plastic bottle ever become petrol again? Before we can turn plastic back into fuel, we need to understand how it became plastic in the first place. Because the answer begins somewhere surprisingly familiar. Crude oil. Crude oil isn't just one substance, it's an enormous mixture of hydrocarbons. When a refinery separates these molecules by their boiling points, it gets a whole family of different hydrocarbon fractions. Some will become fuels, others become the raw materials for something completely different. To make plastic, naphtha is first sent into a cracking furnace, where intense heat breaks its long hydrocarbon molecules into smaller ones. The resulting products then pass through cooling and separation units, where different hydrocarbons are separated. Among them is ethylene, one of the most important building blocks for making polymers. The ethylene is then sent into a polymerization reactor, where, under carefully controlled conditions, individual ethylene molecules link together to form long chains of hydrocarbons called polymers. And from these polymers, the plastic materials we use every day can eventually be made. Here, a very interesting question. If we turn liquid fuel into plastic, can we reverse this process? After decades of mass plastic production, the world was left with an enormous problem: plastic waste. It was cheap to produce, but incredibly difficult to deal with at such a massive scale. Recycling could recover some of it, but mixed, contaminated, and difficult to recycle plastics remained a major challenge. After years of research, scientists developed a fascinating approach: plastic pyrolysis. We begin with the plastic feed entering the pyrolysis reactor. Inside, the plastic is heated to a very high temperature in the absence of oxygen, so instead of burning, it begins to break down. As the temperature rises, the solid plastic first melts into a thick liquid. Then, at around 400 degrees Celsius, the intense heat breaks the long polymer chains into smaller hydrocarbon molecules, producing hot hydrocarbon vapors. The hot vapors then travel into the cooling and separation tower, where the temperature is carefully controlled. As they cool, the heavier hydrocarbons condense first, followed by medium and lighter hydrocarbons at progressively lower temperatures. The result is a mixture of different liquid oil fractions, separated according to their boiling and condensation behavior. So, after the plastic has gone through pyrolysis, and the vapors have been cooled and separated, we are left with three main types of liquid fractions. But what are these fractions actually used for? The light fraction contains relatively short-chain hydrocarbons. This range is similar to gasoline and naphtha. After suitable processing, it can be used for gasoline-range fuel applications, or as a feedstock for producing new plastics and solvents. Then comes the medium fraction. Its hydrocarbons chain are somewhat longer. This range produces diesel and light fuel oil, making it suitable for applications such as generators and fuel for vehicles after appropriate processing. And finally, we have the heavy fraction. These contain much longer hydrocarbon chains. Depending on their exact composition, they can be used as heavy fuel oil, wax-like materials, or refinery feedstock. But there's something else we should ask. What could we actually do with this technology? Every day, enormous amounts of plastic waste are generated around us. And once that plastic has been used, getting rid of it isn't always easy. And this is where pyrolysis becomes interesting. Instead of simply treating certain plastic waste as something to throw away, we can potentially treat it as a source of fuel. And economically, this creates an interesting possibility. It has some disadvantages, like yield of liquid oil, highly depends the type of plastic used, and also the process demands high energy cost. But still, it is a very profitable industry if built at a large scale. So perhaps the real question isn't, could this plastic bottle ever become petrol again? It's how many times we can give its carbon another useful life.